let us look at general information on quenchants. Let's have an insight on the various subtopics such as Hardcastle, Petrofer and Quenching, physical and chemical data of the various quenchants, the quenching process including the vapor blanket phase, the boiling phase, and the convection phase. We will also discuss the effect of bath temperature on the quenching process, aging resistance, service life and consumption, the safety precautions required, maintenance and monitoring of quenchants, and finally, cleaning heat-treated components. Well, now we begin with the first subtopic under general information on quenchants, Hardcastle, Petrofer and Quenching. The metallurgical properties of heat-treated steel components are primarily dependent on the following factors: austenitizing conditions, hardenability of the steel, and quenching process used. Well, to begin with austenitizing conditions, the austenitizing conditions like hardening temperature, furnace atmosphere, hardenability of the steel. The hardenability of the steel, which mainly depends on the chemistry or grade of steel, and percentage of alloying elements. Quenching process. The quenching process used, whether carburizing, through hardening, or induction hardening. Modern heat treatment processes are continually making new demands on quenching fluids, and Hardcastle Petrofer's extensive development programs ensure that our product technology is more than capable of meeting these new requirements. These programs are designed not only to improve the technical properties of our quenchants, but also to provide economic and environmental benefits. At Hardcastle Petrofer, we use the latest technology. We are constantly screening new raw materials for their suitability for use in quenchants, and our existing product range is reviewed continually to ensure that the best available technology is used. We also collaborate with equipment manufacturers and our valued customers for developing new products according to their specific need. By using this approach, backed by our in-house capability and know-how, we are able to offer the most comprehensive range of quenchants available today. Comprehensive range of available quenchants: medium-speed quenching oils, accelerated quenching oils, bright quenching oils, hot quenching oils, vacuum quenching oils, water-based polymer quenchants, molten salt baths, and customized quenching oils. By having our own extensive development facilities and a complete range of products, we can ensure that the best solution is delivered to meet customers' needs. Many factors are important in choosing the most suitable quenchants. Hardenability of steel. Hardenability refers to the capacity of hardening or hardening depth in a steel rather than the maximum attainable hardness value. Alloying elements like magnesium, chrome, nickel, molybdenum, vanadium increase hardenability. Alloy steels have significantly higher hardenability as compared to the plain carbon steels. Hardenability of any steel is evaluated by Jomini end quench test. Component details, that is, component shape or geometry such as gears, bolts and nuts, bearings, steel bars, forgings of crankshaft, connecting rods, stub axles and knuckles. Metallurgical properties required like hardness, case depth, yield strength, impact values, etc. Furnace equipment: bogie furnace, pit furnace, and sealed quench furnace. Post-treatment: washing machine. Environmental issues. As many variables often have to be considered, it is important that a comprehensive knowledge of the quenchant is available. That is, physical and chemical data, quenching properties, thermal and aging stability, physiological and ecological properties. Okay, now we shall move on to discuss one of the most important aspects of selection of suitable quenchants: physical and chemical data. Important data for identification of quenching oils typically are viscosity, flash point, specific gravity. Let's understand the relation of viscosity and oil bath temperature. By maintaining the correct bath temperature, one can achieve optimum working viscosity of the quenching oil. When the quenchant temperature is too low, it can result in high viscosity, reduced agitation, and increased drag-out loss. When the quenchant temperature becomes too high, it can cause unnecessary smoke formation as well as increased fire hazard. Let's refer to the graph of viscosity versus application temperature of the quenching oils. Quenching oil temperature should ensure optimal viscosity, which is generally in the range of 5 to 15 centistokes. The red line indicates low viscosity accelerated quenching oil. The blue line indicates a medium fast speed quenching oil having high vaporization stability. And the yellow line indicates hot quenching oils. Importance of product flashpoint. It limits the application temperature range. Typically, the application temperature upper limit should be approximately 60 degrees Celsius below the oil's flashpoint. Specific gravity of a pure mineral oil can give an indication of its origin. However, it can be significantly modified by additives, and therefore, the quality of a quenching oil cannot be determined on the basis of its specific gravity. Let's catch up on the next topic, the quenching process. The quenching process. A quenchant is characterized primarily by its quenching properties, and these are difficult to describe in words. Descriptions such as severe quench or mild quench are of little use in technological era. The quenching process or cooling rates can, however, be studied using test probes such as nickel and nickel alloy probes using cylinders 12.5 mm diameter as per ISO 9950, or alternatively steel probes 3 to 80 mm diameter as per Meinhardt method, or a silver ball 20 mm diameter as per MPI silver ball method, or silver cylinders 8 or 16 mm diameter as per SETIM method. We use the IVF quenchometer for cooling curve analysis, which has an Inconel probe of 12.5 mm diameter. Usually, the cooling effect of a quenchant is shown by charting temperature versus time, or the rate of cooling versus temperature. The following graph shows the relationship between these two methods. We now look at the relationship between temperature versus time. The red line on the cooling time graph shows higher speed, as compared to the yellow line showing lower cooling speed of the product. Now we move on to the rate of cooling curve on the right side of the diagram. Here, the red line indicates the typical cooling characteristics of the faster quenching oil, as compared to the yellow line, which depicts slower cooling rate of the quenching oil. We now move on to the study of the three phases of quenching. A vapor blanket is formed on the component immediately after immersion in the quenchant. This vapor layer acts as an insulator because of its low thermal conductivity, and therefore the cooling rate in this phase is low. The duration of this phase depends essentially upon the quenchant's composition. Our accelerated quenching oils have a very short vapor blanket phase, and in this respect are superior to most other quenching oils. A short vapor blanket phase is not only necessary to avoid undesirable pre-transformation microstructures, but it also ensures a steady lowering of temperature on the entire surface of the component, thus minimizing thermal stress and distortion. After a period of time, depending upon the quenchant and component geometry, the vapor blanket starts to break down and the boiling phase begins. Heat is conducted away at an increasing rate by evaporation of the quenchant at the component surface. The rate of cooling reaches its maximum, and as the surface temperature falls, boiling becomes weaker and finally ceases. In the last phase of cooling, heat is conducted away only by convection. Consequently, cooling in this phase can be significantly affected by circulation of the quenchant. A high degree of cooling in the convection phase will result in deeper hardening of the component. Well, for evaluation of the cooling curves, the following points are therefore important. Duration of the vapor blanket phase, temperature range of the boiling phase, the cooling rate during the convection phase, and the temperature at which it begins. A shorter vapor phase gives fast and homogeneous cooling of the entire surface of the workpiece. wide boiling phase gives good heat extraction in large diameter components. Cooling in the convection phase can be influenced by circulation of the quenchants. Significance of maximum cooling rate. The maximum cooling rate can be used to compare various quenchants. The relation of the steep slope of temperature versus time curve and its position in relation to the time-temperature transformation diagram is of utmost importance. The green lines show the typical time-temperature transformation diagram of a plain carbon steel grade. The cooling speed curves of two different quenching oils are shown in red and yellow. The red line shows quenching oil having a short vapor phase, and the yellow line indicates the quenching oil having longer vapor phase. A short vapor blanket phase is necessary when quenching low alloy or plain carbon steels, as only a few seconds or, in extreme cases, fractions of a second are available for the temperature to fall below the critical temperature range of approximately 600 to 500 degrees Celsius. If this requirement is not met, undesirable soft structures such as bainite, pearlite, trustite, and possibly ferrite occur, resulting in lower hardness. For the hardening of alloy steels, where the TTT curve lies further to the right, the duration of the vapor phase is less critical. But one should also consider that uniform cooling of the surface reduces thermal stress and distortion, as discussed earlier. In the following topic, we will learn the effect of bath temperature on the quenching process. The graph shows the effect of average cooling rate when the temperature of the job is in the range of 800 to 300 degrees Celsius, measured in degrees centigrade per second, plotted against the quenchant bath temperature. For all practical purposes, quenching oils do not change their cooling characteristics when their bath temperature remains within the recommended working range. Only extremely low or greatly elevated temperatures lead to lengthening of the vapor phase, and thus a change in the performance of the oil. However, aqueous or water-based quenchants are affected significantly by bath temperature. This is caused by the much smaller difference between the working temperature range and the boiling range of aqueous solutions in comparison with oils. Water boils at about 100 degrees Celsius, whereas oils boil from about 300 degrees Celsius upward. Consequently, when aqueous media are being used, bath temperatures must be kept constant within relatively narrow limits. The graph shows the influence of bath temperature on the quenching performance of several quenching fluids. The average cooling rate of water, additive salt in water, and up-concentration polymer quenchant reduces as bath temperature increases. Whereas, in the case of low viscosity accelerated quenching oil and hot quenching oil, the average cooling rate remains almost same throughout its operating temperature range. Let us once again review the influence of bath temperature on the quenching properties. For quenching oils, the bath temperature has insignificant influence when operated within its recommended viscosity range. For polymer solutions, bath temperatures have a considerable impact on quenching properties. This can be used advantageously when quenching tool or die steels, and slow cooling is required. While quenching in water, the temperature of water bath has a distinct effect on the quenching characteristics. The control of bath temperature plays a significant role in ensuring uniform quenching characteristics throughout the quenching cycle. For control of the bath temperature, we can consider heat balance calculation as shown, where the formula indicates heat input from the metal is transferred to the quenchant. It can be used to design the cooling arrangement required to maintain a constant temperature. The temperature of the quenching oil must be maintained within the recommended range, as it can significantly influence the life of the oil, drag-out loss, and distortion of components. Various types of heat exchangers like shell and tube, plate type, forced air-cooled can be used for control of temperature. The screen shows a typical schematic of a plate-type heat exchanger through which hot quenchant is cooled by circulation through the heat exchanger. Now let's move on to a discussion on the aging resistance, service life, and consumption of quenchants in the process. Resistance to evaporation has a considerable effect on consumption and thus on oil bath economics. Experience has shown that on batch quenching, probably more oil is lost through evaporation than through drag-out by the components. Aging resistance is, however, of the greatest importance in determining the economics of any oil bath. Oils having poor oxidation resistance will form a sludge after a short period in use, and this normally results in deposits in the cooler, the coldest place in the quenching bath. Ultimately, discoloration appears on the surface of the treated components, which is either difficult or impossible to remove. At this stage, replacement of the oils is unavoidable. During the development of our quenching oils, we have placed great emphasis on their resistance to oxidation aging by using highly stable base oils and, in many cases, sophisticated proprietary additive packages. The image on the left shows quenching oil having good aging resistance after an oxidation aging test. The image on the right shows quenching oil with poor aging resistance after an oxidation test. Now, let us discuss the advantages of using a quenchant having stable parameters. The high evaporation stability of oil helps in reduction of smoke and also the consumption due to lower evaporation. The good oxidation stability of the oil provides better service life and helps reduce sludge formation. The oils having high thermal stability significantly reduces smoke and helps retain typical quenching properties for a longer period. Several important points need to be observed when using an oil bath in order to achieve the optimum working conditions. In order to keep the thermal loading within limits and also to avoid severe variations in the working temperature of the bath, a relationship between the weight of the batch or hourly throughput of the furnace and the volume of quenchant must be maintained. Consequently, the following values can be used as a guide to the relationship between the weight of quenching oil and the gross weight of the batch to be quenched. Open oil baths 10:1. Sealed furnaces 10:1 to 7:1. Hot quenching oils used at their highest temperatures 10:1 to 15:1. These values can also be used where quenching of small batches at short intervals takes place, and the hourly throughput of steel is then used in the calculation. Now we see the effect of loading pattern. This relationship depends upon the conditions of the use of the oil and upon the size of the components. Larger components which take longer to cool cause a lower thermal loading to the oil bath than tightly packed batches of small components which give off their heat rapidly. The cooling and the heating elements of the heat exchanger should not be made of copper, as this acts as a catalyst in the oxidation of all mineral oil products. The level of agitation in the system must not be excessive, such that air is drawn into the oil. This condition will result in foaming and increased oxidation of the oil. The heating area loading of the heating elements should be limited to about 1 watt per centimeter square. If a higher loading is used, good movement of oil in the area of the elements must be maintained to avoid overheating. The life of water-miscible quenchants is usually limited by several factors. In the case of induction hardening operations, the solution has to be replaced after periodic intervals due to the effects of contaminations from previous processes. The thermal loading can also take its toll in the long term. In view of this, and the need to control the concentration of solution, monitoring is required for polymer quenchant solutions. Now, we need to deal with the most important aspect, safety precautions. Let's have a brief discussion on it. While operating quenching baths with oils, we need to exercise certain safety precautions to avoid quench fires. Ingress of water into quenching oil bath, typically through a leaking cooler or as a condensate, does create a special hazard. As little as 0.1 to 0.3% water contamination can considerably increase the fire hazard, as well as significantly change the quenching characteristics of the oil. Quenching oils are combustible liquids, and in the quenching process, the temperature of the components being treated is usually well above the flash point of the oil. Simple precautions are required so that there are no fire hazards in practice. Immersing the charge completely in the quenching oil is essential to avoid fire hazard. Maintaining the quench oil level to ensure sufficient head of quenching oil above the surface of the components is also recommended. It is advisable to turn on the agitation of quenching oil before start and during the quenching cycle. Contamination with fire extinguisher can change the quenching characteristic and other properties of the quenching oils. Drag-in of soot in the quenching oil can lead to stains on the component surface. Now, let's take a look at maintenance and monitoring. Aqueous quenchants must be carefully monitored with respect to both the operating temperature and the concentration of the solution. Relevant instructions have to be carefully followed to ensure successful result. Under normal operating conditions, quenching oils do not require regular monitoring. Attention should, however, be paid to ensure the working temperature of the oil is maintained and that the temperature never exceeds one which is at least 60 degrees Celsius below the oil's flash point. The oil should also be regularly checked for water contamination. We recommend checking oil baths at least annually and water-miscible quenchants at shorter intervals depending upon the operating conditions. Well, let me now brief you on cleaning heat-treated components. When water-miscible quenchants are used, post-cleaning of the heat-treated components is often unnecessary, even before tempering. However, when high concentrations are being used, rinsing of the components is recommended. Hardcastle Petrofer's quenching oils will produce hardened components with a bright finish, provided, of course, there was no prior surface oxidation. The components are suitable for further treatment, such as electroplating, without problems. Oil residues do not burn into the surface of the metal and therefore can be easily removed. Removal of quenching oil generally requires the use of hot aqueous cleaners or use of water-washable quenching oil. Degreasing with solvents in a soak tank or in vapor is also possible. The hot cleaner chosen should be formulated to provide rapid release of the quenching oil so that it can be easily removed from the wash tank. Hardcastle Petrofer has developed High Clean for this purpose, thus enabling wash water to be used for longer periods with savings in the disposal costs. For removal of separated oil, the use of weir systems or oil skimmers is recommended. Even emulsions from water-washable quenching oils are destabilized when small quantities of High Clean, 0.5 to 2%, are added to the washing water. Centrifuges also enable very good oil separation from the wash and can be used for both conventional and water-washable quenching oils. It is essential to exercise certain precautions to avoid negative influences in the cleaning process. When agitation is inadequate, it may influence the cleaning of parts, particularly when the parts to be cleaned are immersed in the bath in a tightly packed condition. Care has to be taken to ensure oil residues on the parts are properly cleaned by the use of suitable cleaner, as otherwise these residues can cause smoke formation during subsequent tempering processes. The health of the cleaner bath is required to be ensured by proper skimming, so that the parts after cleaning do not get coated again with the oil layer floating on top of the cleaner bath. Well, we come to the end of general information on quenchants. Hope it was an informative session.